Okay, so on Friday, we defined a projectile as any object in unpowered flight within the Earth's gravitational field. Okay? Now, the Earth's gravitational field extends a long way from the Earth. Okay? By the strictest definition of it, the moon is a projectile. It's also a satellite. All satellites are projectiles. Okay? And we'll learn a little bit more about this in Unit 3 when we talk about satellite motion. But the reason that an orbit is circular is because it is a complete projectile arc. Okay? We talked about on Friday how a projectile will follow an arc like this. Okay? If it's shot at an angle, okay, it'll follow an arc like that. Well, a satellite orbits the Earth because it's going so fast that its arc completes itself and it actually never comes back down to Earth. Okay? I mean, after all, how do you get a satellite into orbit? You put it on a rocket and you make it go really, really fast. Okay? And so essentially it's just a really fast projectile. Once the rocket is gone, it's an object in unpowered flight in the Earth's gravitational field. Its arc just never encounters the ground. Okay? It just completes the circle and it just orbits the Earth as a result. Okay? So what we're going to be looking at today is we're going to start out with projectiles that are projected horizontally. All right? So a car drives off a cliff. A person runs off a diving board. Okay? Things like that. Anywhere where the initial action is purely horizontal. There's no angle above the ground to any of these. They're straight off. Okay? So that's what we're going to look at today first. Okay? Those are a little bit more simple because we don't have to do any trigonometry like we would if we had something like this, okay, where the object is projected at an angle, which we may get to today as well. We'll see how it goes. Okay? All right. Last week when we were talking about projectiles and we said if you drove a car off a cliff, and I was talking about the Thelma and Louise movie that I couldn't stand, okay? If you drive straight off a cliff like this, what's your initial vertical velocity? 0. Okay? Your initial vertical velocity at time 0, the instant you leave the cliff, okay? You're not moving vertically. All of your movement is horizontal at that point. Okay? And that's the important thing we have to remember about horizontally projected projectiles, is that initially they are not moving vertically. Okay? They're going to move vertically because of gravity. And that's the other part of this. All projectile motion problems consist of 2 dimensions. The vertical dimension, which is undergoing accelerated motion, and the horizontal dimension, which is undergoing motion at a constant velocity. Okay? So if something goes off this cliff, it's going to do this. Okay? It's simply going to arc down to the ground. Initially, more of that velocity will be horizontal. Okay? But the vertical part will quickly take over as the object accelerates vertically, but travels at a constant velocity horizontally. Okay? Everybody all right with that idea? See a bunch of you writing this down. Don't worry, we're going to do this in an example here in just a sec. Oh.
What's after the V?
Oh, that's vertical. It's supposed to be an E. I have to calibrate this. I keep writing and it's drawing where I'm not writing. It's really annoying. Okay. So on this question, we've got a person who's running off a cliff at 8 meters per second. They're going to fall to the water, okay? And they're going to hit the water 15 meters horizontally from the base of the cliff. Okay? So it's always a good idea to draw these ones out. Okay, so the person's running off the cliff horizontally at 8 meters per second. Right? So from a vertical perspective, how fast are they going when they're right there? Zero. Right. Okay? They're going 0 meters per second. Their initial vertical velocity, okay, if they run horizontally off the cliff, their initial vertical velocity is 0. Okay? What else do I know about the vertical part of their movement? Right, they're accelerating. Now I can make it negative, but I don't have to. And the reason I don't have to is I'm not changing direction. It's always going to be down. If you want to make it negative, just make sure you make every other thing that's down, which will be everything, negative. Okay? That's why you don't really have to for this type. For the other type where it's projected upwards initially, you do have to make it negative for that because it is going to change direction. Okay, so I got VI, I've got A, and they want to know how high the cliff is, which would be the vertical displacement of the person by the time they're done. Agreed? Okay, so that's what I'm looking for. I'm looking for the vertical displacement. Now, from a horizontal perspective, I know the following things. I know the constant velocity at which they're going to travel, and it's 8 meters per second. Okay. I also know they're going to do this, and that this distance here is 15 meters. All right, that's all I know right now. If I want to find my vertical displacement, I have VI and I have acceleration. I need one more thing if I'm going to be able to calculate D. What is it? Time. I could also do it if I knew what VF was, but I don't know what that is. Okay? I also don't know what the time is. So I got to have a way to figure out one or the other of those two things, because then I would have a formula that I could use to get the distance. Okay? So I got to look over here at my horizontal information. Now we just said a minute ago that horizontally it's going to travel at a constant velocity, which means that formula applies to the horizontal part of my movement. So what can I calculate right now with the horizontal information? Time. Is the time going to be the same for the horizontal and the vertical parts? It is. Just like it is in those boat questions we learned about. Okay? The amount of time it takes me to cross the river is the amount of time I go down the river. They're the same. They're happening at the same time. I mean, once they hit the water, they're not doing either one of those things anymore. They're not moving horizontally and they're not moving vertically anymore once they hit the water. Okay? So the time is the same for both parts. So I can use either side to find the time, and then I can use it for the other. So that's what I'm going to do. I can find the time using T equals D over V. So 15 over 8. Okay, so I got 1.875 seconds is my time here. Okay, that time can be used over here because the time it moves horizontally and the time it moves vertically are the same. Now can I calculate D? Okay. And I'm going to use this formula. D equals VI times T plus 1/2 AT squared. I don't even have to manipulate it. It's already set up to find what I'm looking for. So since VI is 0, I can get rid of that. Okay. And all I have to do is plug in my numbers. 1/2 times 9.81 times 1.875 squared. The cliff is 17 meters tall. Okay. So for these kind of questions, all you have to be able to do is V equals D over T and solve acceleration problems, neither of which has proven overly challenging for anybody. Okay? It's just the context is a little bit different now than it was before. Questions on how that one worked? Now, there's a number of different ways that I can ask a question like this. I could, instead of asking you to find the height of the cliff, I could give you the height of the cliff and ask you to find out how far from the base of the cliff the person would land. Or I could give you the height of the cliff, how far from the base of the cliff the person lands, and ask you to calculate how fast they were running when they ran off the cliff. Okay? It's all going to be the same stuff, it's just going to be in a different order. Okay? You're still solving for something using the stuff from the other side. Now, the thing we almost always have to find in a projectile motion question of any kind is time. Time is probably the most valuable piece of information for any projectile motion problem because it can be used for both the horizontal and the vertical parts of a projectile motion problem. It's the one thing they have in common. All right. So, I'll show you a quick video or two here. So for this one, same idea. Okay, we got a ball. It's rolling off a 1.2 meter high table. Okay, it hits the floor 0.85 meters from the base. What speed did it roll off at? So you're looking for the horizontal speed. Okay, now remember that doesn't change. Right, so you got to look at what you're given, draw it out. Okay, I'll give you a couple minutes to give it a try here. All right, so with this one, we want to start off with just a drawing, okay, of a ball rolling off of a table. Okay, so the table we know is going to travel 1.2 meters vertically. It's going to accelerate at 9.81 meters per second squared. And its initial vertical velocity is what? 0, because it rolls horizontally off the table. All right, so that's what we know vertically. Okay, we're looking for this. How fast did it roll off the table? Okay, so we're looking for horizontal v. We know horizontal distance is 0.85 meters. What do I need if I want to get v? Time. Okay, and as I said in the last question, you're always looking for time. Time's the most important piece of information that you can get in a projectile motion problem. All right, can I get the time with these three pieces of information on the vertical side? Yep. Okay, I'm going to use this formula here. D equals VI times T plus 1/2 AT squared. You know that one I told you never have to use to solve for time, unless VI was 0, which it is. Okay, so now I can solve for T. I'm just going to divide both sides by half of A, and then square root. That'll leave me with T. Okay, so T will equal the square root of 1.2 meters divided by 1/2 times 9.81. And again, if you're going to make the 9.81 negative, you got to make the 1.2 meters negative as well, because they're both down. And if you don't, your calculator gets very upset. It says you can't do what you want to do, which is take the square root of a negative number. Okay, so we got square root of 1.2 divided by 4.905, which is half of 9.81. Okay, so this thing is going to fall for 0.49 seconds, which is something that can come over here. And now I can use it to find V with a simple V equals D over T calculation. 0.85 divided by 0.49. Obviously, I'm going to keep all the decimals. Okay, so I'm going to have my 0.85 divided by 0.49. All right, so we're looking at 1.7 meters per second as our speed that it rolled off the table. Okay, everybody kind of follow what I did there. Right, so I used the vertical information to get a piece of information I didn't have that I needed to do the horizontal part. Okay, and that's what we're always doing. It doesn't matter what type of projectile motion problem we're trying to solve, we're always trying to get something from one component to use for the other component. Questions on that one? Everybody's okay there? All right. Okay, so what we're going to look at now are a few examples of projectile motion that's projected at an angle. Okay, so first one I'm going to show you or talk about has to do with this viral video that was out years ago now, probably like 10 years ago or maybe even more than that. Okay, and it was of this guy who had built a giant slip and slide down the side of this big hill, and then he had a ramp, and he shot himself off the ramp, and he landed in this little kiddie pool, like an impossible distance away. Okay? And this thing, like, people went nuts over this thing because it just looked crazy. Okay? So I'm going to show you that video first, and then we'll kind of look at what would have gone into it, and then I'll show you the Mythbusters busting it. Okay? So, okay, so the idea here is this guy goes down this incredible slope, he builds up an incredible amount of speed, and then flies off the ramp and lands in the tiny little kiddie pool. Now, just from a common sense standpoint, I mean, that kiddie pool, when he was standing in it, was not even up to his waist. So we're not talking about deep water here, okay? There was less than 3 feet of water in there, okay? And he landed in it going really fast. Did you notice that, yes, there was a splash, but that the pool didn't move? Should the pool have probably moved?
Yeah.
Yeah, it should have. Okay? In fact, it should have flipped over, emptied out, and had like this broken person in it. Okay? Because there's no way that much water would have cushioned the impact of you hitting that and then like the pallets underneath it, and like, you would have gone right through the pallets, okay, and onto the ground. Like you would have broken his back at the least, okay, doing that. That amount of water is not going to save your life, okay, in that situation. It's just not enough water. Okay. So basically, what they did is they kind of worked backwards here. They wanted to figure out if I was going to actually do this for real with a bigger pool, okay, I would need to figure out how far this person was going to travel horizontally after leaving the ramp. Agreed? Okay, so here's the stuff that we would know. We would know how fast they would be going when they get to the top of the ramp. That would be a simple law of conservation of energy question like you would have learned in Science 10 with the roller coasters, right? The roller coaster starts up here, how fast is it going when it's here? Okay, you'd very easily be able to figure out how fast you'd be going at the end of the ramp. Okay, so you'd know that. That would be your projected velocity. Now, it's a velocity because it's angled. It has a vertical component and a horizontal component, which I can then use to figure out how far the person will travel horizontally. Okay, so this is the calculation that they would run through. They break this up into its vertical and horizontal parts. Okay. From a vertical perspective, right now I know for sure that the acceleration is 9.81 meters per second squared down. Okay. Everything else I have to calculate. So, with this projected velocity, okay, it's angled 30 degrees above the horizontal. It has a vertical component or a y component and a horizontal or an x component. Can I calculate the two sides of that triangle? I can. It's just like it's just finding vector components, right? You guys had to do that for your assignment that you handed in today. So yeah, we definitely know how to do that. Okay, the vertical part of this represents my initial vertical velocity. I say initial because it's going to change. Okay? As the person flies through the air, the vertical part's going to get slower, okay, until it stops, and then it's going to accelerate back down. So from a vertical perspective, if all I saw was what this person was doing vertically, I'd see an object that goes up in the air and comes straight back down again. Okay, just like throwing something straight up in the air. From a vertical perspective, that's all that's going on. Horizontally, the person's going to travel at a constant speed because there's nothing to speed them up or slow them down. Okay? So let's calculate VI first. So VI is the opposite side. So we'll have the sine of 30 times 20 meters per second. Okay, times the hypotenuse here. Right? So that means that their initial, times 20 meters per second. Okay, so VI is going to be 10 meters per second, and it'll be positive because it'll be up. All right, so when they get launched off of that ramp, they are moving straight upwards at 10 meters per second. they're also moving horizontally at the same time. Everyone okay with that so far? So let's find out what the horizontal part of this is. Okay, we'll call it V horizontal because we know it's not going to change. Okay, that's the x component of this triangle. So what trig function do I use for that? Cos. Right? So I'm going to go cos of 30 degrees times 20 meters per second. All right, so we're looking at 17.3 meters per second. So they're moving horizontally at 17.3 meters per second. Okay, that's around the same speed Usain Bolt runs at when he's at top speed. Would you want to hit something at that speed? No, it would hurt a lot. Okay, it would definitely break bones. Okay, so we don't want that, but that's how fast they're going. Okay, and that's just the horizontal component of it. Remember, there's a vertical component here as well. Okay, if they fly through this arc like this, they're going all the way up and all the way back down. If you watched carefully, the pool was actually level with the top of the ramp because it was actually placed up on a hill. Okay, so they went up and back down the same distance. So their overall displacement vertically ends up being what? Zero. So if I start at 10 meters per second up, go all the way to my maximum height, stop, and then accelerate at exactly the same rate, the exact same distance, how fast am I going when I get back? Same speed. Okay? If I throw this marker up in the air, okay, and it comes back down, I catch it at exactly the same height I tossed it from, it's going to be going exactly the same speed when I catch it, because everything is the same, right? It leaves my hand at 10, it goes up a little ways, okay, comes to a stop, and accelerates back down the same distance at the same rate, so it's got to be going the same speed I threw it at when it comes back. Okay? This is why you don't want to shoot a gun straight up in the air. Actually, in real life, you wouldn't get hurt because the bullet will tumble and won't fall back the same way. Okay? If it was like in a vacuum, you'd want to get out the way. Okay? Because it would come straight back down and would be going the same speed it was fired at when it came back to you. So, yeah, okay, you got to be really careful about that. Okay, so now that we know that, we can say that VF would be negative 10 meters per second for this first. Okay? And unless you're told otherwise, all the projectile motion questions we do, the start and end are level. Okay, they're at the same altitude. All right, so I want to find out where I have to put this pool, which means I need to know how far that person is going to travel horizontally. Horizontally speaking, they're traveling at a constant velocity. So that's the formula I would use. Vertically, obviously, they're accelerating. What do I still need in order to calculate that distance? Time. Can I find time with the information I have in the vertical part? I can. Okay, I just have to use an acceleration formula. This one. Right? I have all of that stuff. Okay? So when it comes right down to it, this type of projectile motion question is very similar to the other one we just did. It just adds in, you got to do 2 trig calculations, okay, before you can get to it. All right, so if we're solving for t, that's going to be VF minus VI over A. So that'll be negative 10 minus 10 divided by negative 9.81. Okay, so we're going to have negative 20 divided by negative 9.81. Okay, so he's in the air for just over 2 seconds, which may not seem like a long time, but it is. Okay, to be flying through the air towards a tiny kiddie pool that won't save you.
On our formula sheet, it's plus, like VI plus VF. Should it be VF minus VI the other way around?
It shouldn't be plus. So are you looking at the one that's D equals VF plus VI over 2?
Yeah.
Okay, I'm not using that formula. I'm using VF minus VI over T. Yeah? Yeah. Yeah, okay. You good? All right. So just over 2 seconds is our flight time, like 2.03. We'll keep all the decimals. Okay? So now that we know that, now we can find d. We're just going to go v times t. So we're going to take that 17.3 and multiply it by 2.03. Okay, so he's going to fly through the air 35 meters. That's a pretty long way to fly. I certainly wouldn't want to land in a tiny little kiddie pool, okay, after having flown that distance off a giant water slide. All right, so is the video real or fake? It's fake. It's fake. Okay, but the Mythbusters still had a fun time trying it. They built this slide, and they tried it. Not with Buster either. Okay, Adam and Jamie both went down the slide into a big lake. Not into a little kiddie pool because they knew that part was crazy. Okay. All right, so I'm going to show you them busting it here. When you had TV shows that had car chases, a lot more thought and effort had to go into making the jumps work. If you had a video clip or a show where a car was going to jump over something. Okay? Now, you just CG it. Okay? It's super easy. You want to make the car look like it's doing something incredible, you just put it in a computer and make it happen. But before CGI, people had to do the calculations, build the ramps, have a stunt driver, okay, in the vehicle and actually pull off the jump. Now, you didn't want to waste it because you had to do it right, or you had to do it with a new car, possibly you have to do it with a new stuntman, okay? You know, all that kind of stuff. So, you know, a lot more calculating and preparation would go into getting these shots. Nowadays, you just run the car off the ramp, so you get that initial shot and sound, and then after that, it's all done in the editing. Okay? So, some issues with getting good shots of a car making a jump. First off, the car is going to get broken. At the beginning, not before. Like at the end, it's going to be total, but you're actually going to break it at the beginning as well. Okay? And I'm going to show you some clips here from this classic show that's no longer on TV called The Dukes of Hazzard. Not the movie, which was a travesty, if you've seen the movie. Okay? The original show was actually a pretty wholesome show. But in this show, these cousins, Bo and Luke Duke, okay, were constantly having to run away from the law because the law was always trying to set them up. They had been caught moonshining or running moonshine, which is legal liquor, okay, and they'd gone to jail and they were on parole, and the sheriff didn't like them, so he was always trying to catch them in something, and they weren't ever really doing anything, but you know, it's for dramatic purposes. Anyway, in this place where the show is set, there are all kinds of dirt roads that apparently just don't have bridges, so you have to jump over lots of stuff. Okay, and you have to do it all the time. It was like this was like the key point of the show was how many times were they going to jump the awesome car that they had, okay, in any given episode. So we're going to watch a few jumps that they did. I actually found a clip on YouTube that is every single jump of the General Lee in like the 7 seasons of the show. Okay, we won't watch the whole thing because it takes forever because it's actually that many. By the end of the show's run, they had run out of 69 Chargers to jump. Okay, they had wrecked hundreds of these beautiful cars already, and they had actually started shooting it with Challengers, which had similar bodywork and from the right angle looked enough like it that they could pull it off. Okay, they had actually straightened the frames on a bunch of the previous jump cars enough to use them again, and you can actually see sometimes in the shots when they're reusing a car because you can see it's dented, okay, or you can see that like the hood is strapped down, okay, so it doesn't fly up. But some of them got reused a few times. Okay. You can also see when you watch this clip, sometimes they don't cut away quickly enough because the problem with jumping a car is that it's going to go up and then it's going to nose down on the other side. The steeper the launch angle, the more likely it is to nose down on the landing side. And then of course it doesn't look legit, okay, when it lands. Right, so what they usually will do is just launch the car, and then just before it hits the ground, they cut away, and all you see the next shot is the car driving away, and it's all right. Okay, so it's all a lot of editing room kind of trickery, but remember, there was no CG. Every time one of these cars is jumped, a beautiful 69 Charger dies. Okay, All right.